Hello and welcome back to another lecture from organic chemistry. I want to practice more example about how to use splitting and to find the structure of the unknown sample. Okay, so they gave us a C5H12O. That's going to be a saturated compound because the HDI or hydrogen index, hydrogen deficiency index number is going to be equal to 0. So I don't have a pi or a ring. And also, if I highlight the number of the signals, as you see, we have 4 signals. And so that one is like that we have at least 4 carbons that they are carrying hydrogens and they are not identical. Okay, they are not identical. Or maybe we have 4 like in places that they have hydrogen and they are not identical again. Okay. Now, how do I use like those splitting? And let's look to 3H and 6H. The 3H is telling us that we might deal with CH3. And how about the 6H? That's also CH3, but I might have 2 of them. Okay. Now the splitting is telling me that this one is singlet. So I have singlet for 6 hydrogen. That means maybe I have 2 methyl, and those 2 methyls are terminal. And the neighbor carbon has no hydrogen attached to it. And what's one possibility for it? How about this? A carbon that has a CH3, okay, and neighbor carbon should not have any hydrogen. I'm talking about this one. Should not have any hydrogen. Forgive me. I'm talking about this carbon. That carbon should not have any hydrogen sitting on it. Otherwise, it will split it. Okay, and the 3 hydrogen says got split to 3 peaks. So I'm gonna say this is a methyl group that has a neighbor, and the neighbor must be CH2 because carbon of the highlighted or the one with a star, with the star, it will get split by 2 hydrogen and -1. I have 2 hydrogen, so 2 plus 1, it will give me triplet. And signal is gonna have area equal to 3 hydrogen. And how about this peak? That peak says the integration for it is equal to 2 and got split to quartet. What does it mean? It means it's a CH2 that has neighbor. The neighbor must be CH3. Okay, so we have 3 hydrogen on the neighbor carbon. They will split the CH2 to quartet. And so I'm going to see a signal quartet that has area equal to 2 hydrogen. Okay, now let's put, okay, and now forgive me before I go to the next one. This one is singlet and is 1 hydrogen. So it's a singlet and 1 hydrogen. And what's the possibility for it? The possibility maybe is OH. That's one possibility. Another possibility maybe is a CH. And then, okay, we have groups there, whatever they are, they don't have hydrogen on them. That's one possibility. But clearly, we need way more carbon to get such a tertiary hydrogen, technically. Okay, and I drew all those possible, structures. And I have to say this one: we're supposed to get 4 signals. And so I tried to move the OH in different carbons, and also I moved methyl groups to get different isomers. And I'm gonna look for structures that they have only 4 signals. I got only 2 of them, and I put a star close to them. Now let's go after multiplicity. Okay, what should I get? Okay, 1, 2, 3, 4. Those are the sources. Okay, and let's call this one 1, 2, 3, 4. Okay, for number 1 is a methyl, and its neighbor is 2CH2. So for CH3, I'm gonna get double. Okay, so this one will get split to 2 peaks, double, and the area for it, okay, the area for it is going to give me technically 3 hydrogen. And remember, because we have 2 methyls, there's a mirror there. I'm talking about this methyl group. Forgive me. I'm talking about these 2 methyl. We have 1 methyl here and 1 methyl there, so it will be doublet. But area, it will have 6 hydrogen. Okay, and how about CH2? CH2 it will get split to by methyl and hydrogen that we have here. So for CH2, okay, splitting, we will get doublet, okay, and then those doublet they will be split to in a quartet, or you get a quartet and a quartet. Each peak it will be split to 2, and so we get multi. And how about the area? We have 4 hydrogen, so I go 4 hydrogen. And how about the CH? Okay, CH. Talking about this one, and let's see that one. Okay, we're gonna get. We have neighbor, and the neighbor is gonna be CH2. And we have 2 of them, so they will split it to quintet. So we get quintet. and that's going to give me area equal to 1 hydrogen. Okay. And how about OH? The OH, it will be singlet, 1 hydrogen. Okay, so we got doublet, multi, quintet, and singlet. There is no triplet. Okay, as you see, there is no triplet. And so I don't see a triplet here. Well, this one, it says triplet and quartet. So that's one sign that maybe this is not the structure. How about next one? Next one, we have 2 methyls, and they are identical. And do we have a neighbor H? No, there is no neighbor H. So I'm going to get a singlet peak for 6 hydrogens. That's 1. And next, how about this? This one, it will be splitted by the methyl. Which methyl? This methyl. And because we have 3 hydrogen there, I'm going to get quad. And that's going to split, and that's going to have area equal to 2 hydrogen. And how about the OH? OH, it will be singlet, and it's 1 hydrogen. What else? Last one is going to be the methyl. This methyl, that's going to be doublet, and 2 hydrogen. Okay, so I got singlet, 6 hydrogen. And here you go, singlet, 6 hydrogen. I got quartet, 2 hydrogen, and 2 hydrogen, forgive me. The 2 hydrogen, we got it, quartet. And how about this? 3 hydrogen, supposed to be triplet. Let's see, 3 hydrogen and triplet. Don't forget, last one I made a mistake and I wrote 2. This one is supposed to be triplet, not double. This one is going to be triplet, because we have CH2 as a neighbor, and area 2 will be 3 hydrogen. So it will be triplet and 3 hydrogen, and that's going to be my correct answer. We have a term that we call it, we call it splitting and coupling, or J value. What's the J value? Okay, and it depends, how many hydrogen you have as neighbor. Those hydrogen, they will affect the magnetic field that you feel. Okay, but also you will apply the same effect on them. And if they are splitting my peaks, let's say by, for example, gap of, let's say 1 ppm, and then I'm going to say their peaks also will be splitted by the same magnitude. So any force that they are applying on me, they will feel the same force from my side. And in order to get those fine, splitting, it's better to have a stronger magnetic field. So the machine that we are using is going to be, instead of 60 megahertz, might go to 400 or 500. As the magnetic field of the instrument gets bigger and bigger, you will have a better chance to see those splitting. Those are really, really critical when you are dealing with bio sample, protein, and you want to study the interaction between let's say, component of that protein. You need to push this number maybe to 800 or higher to see all those fine interactions. And for example, when it's 60, I have overlap between signals from B and also C. They are falling in the same area, and as you see, integration is going to be really off, and so you cannot differentiate them. But if you increase the strength of the magnet of that NMR, now you will have a bigger gap between B and C, and the integration is going to be really easy job to do it. So we can read this area without really including area for C. So the integration, it will be way, way more accurate. Okay. Next thing is, as I said, okay, any force that you apply to your neighbor will apply the same force back to you. And so the J value here is going to be exactly the same J value that you see for the triplet. And so the CH2, any force that you're applying to the methyl will send it back, and it will split it with the same J value. Now, if you see a peak that is a singlet, and it has like it has an integration equal to 9, you have high chance that there is a tertiary butyl group in the structure of that molecule. And if it says 6, in that case, you might deal with, maybe you're dealing with 2 methyl groups, and now you have to look at the multiplicity of them. And if the multiplicity is, singlet, that means that there is no neighbor hydrogen. But if there is if there is splitting there, then I can say there is a hydrogen, there is a neighbor hydrogen. And for methyl group here, I can see that is doublet, and that's a sign that we have a neighbor hydrogen, and it can be like an isopropyl, for example, in the group. And so I'm going to say this one will be doublet, and I will have 6 hydrogen here. And how about that CH? That CH is neighbor to 6 hydrogen. So 6 hydrogen plus 1, or N plus 1, it will turn it to 7 peaks. And then as you see, I have 7 tiny peaks. Some of them may be hard to really to see them or catch them. And okay, one more example that I want to practice here. I see 4 peaks, and clearly we have A, B, C, D. Like, let's say how to sign them. And the integration, it says 3, 3, 1, 1. And like D is maybe the easiest one to pick. The reason for it, D is attached to electronegative element. So D is going to be 3 hydrogen, and it will be singlet. And while A, it will be 3 hydrogen, but because it's neighbor to C, it will turn to doublet. So 2 doublet, but the area will be equal to 3 hydrogen, and it will show up in lower ppm or chemical shift than D. So this is going to be A, and that's D. Again, D because it's attached to this oxygen. Now, how about C and B? How do I differentiate those? For a second, move the double bond here and see what will happen. If you move the double bond there, this is going to happen. I will have a double bond here and a positive charge there, and I have this HC. So HC is sitting on a carbon that has a positive charge. And so I'm going to say that one, it will be really de-shielded, and it means it's going to show up in higher ppm. So that's going to be C, and this one, it will be B. Okay.